polygon and let L be a length. So this is still just the intersection of two now circles of radius 1 here. Then if the perimeters are the same, then the length is going to have the smallest area. So here I already made a few simplifications. So as we mentioned last time, that we can always approximate the lambda convex body by this lambda convex polytope. So in this case, I'm going to deal with the problem just for the polytopes in R2. So in R2, this is really just the intersection of circles. And I also chose them all to be of radius 1, since everything is homogeneous, because of homogeneity here. So I can choose whatever lambda I want. So for simplicity, I'm choosing lambda to be equal to 1. Okay? So this is the thing that we are going to prove. So what the general idea? So the general idea, we somehow want to minimize the volume under this surface area constraint. In this case, minimize the area under the perimeter constraint. So in order to minimize, I want to connect them somehow. And the question, how do I connect them? So to connect them, I am going to use the certain type of bodies, so the so-called inner parallel bodies. So this is the notion that is again independent of dimension. It doesn't have to be in R2, it can be in any dimension Rn. And what does it say? So it says that if I take some parameter, I say that it's non-negative parameter, I can define the body, I'm going to denote it as k sub t, which is k minus t ball, but what it really means, it means that I'm looking at all the points, and I'm going to define here in Rn, because it doesn't really matter, so such that the shifts of all the balls of radius t sit inside body k. So how one can also think about this is that I take the body k and I step inside here along the normal vectors at the boundary by the distance t. Okay, and that's the inner parallel body that what I'm getting. Now, of course, if I think in this way, then if I step very far inside, I might not get any body at all. I might step too far and there is nothing left. So how far can I step inside?
Is it guaranteed that the inner body is always convex as well? Or?
Yes, so in this way it is always convex, yes. Yeah. So, right, so how far can I step inside, right? So to step inside, I can look at the following parameter that I can associate with the body. So when I have a body k, I have a bunch of balls sitting inside of it. So there is a variety of balls that I can fit inside. What I can do, I can choose the ball, the largest ball that I can fit inside the body k. Okay, and the radius of this largest ball, so let's say that this is my largest ball, then the radius of this largest ball is denoted by r of k, and hold in radius of k, which is the radius of the largest ball inside K. So of course the largest ball here doesn't have to be unique. There is a situation where there can be many of them. So for example, if you think about the rectangle, right? In the rectangle I can fit the ball here, right? But then it's the same ball here and so on, right? So the in ball itself doesn't have to be unique, but then we're choosing just this largest in radius. And if my parameter changes up to the in radius, then I will have always non-empty set here. Okay? Another thing to mention that if the parameter is equal to the in radius, then we might have a situation where we have degenerate bodies. So we might have a point. For example, when I think about the ball, if I go inside by the radius, what I'm left with at the time r of k is a point. Right? Or I can have maybe some interval, right, line segment or something like that. But the body, so it's going to be non-empty, but it's going to be degenerate. Okay, so that's going to be important. Okay, so then what do I know? So there is a way to connect then the volume and write it as the integral from 0 to the in radius of the surface areas of these inner parallel bodies. So I'm going to explain where it's coming from, but the idea is that if I look at the volume, I have my layers, which are these inner parallel bodies, and I integrate over all these layers, it should give me the volume. So this is intuitively should be believable that something like that should hold. But where is this coming from? So this follows from following fact. So what is known is that the derivative of the volume of inner parallel body is always equal to minus its surface area. Okay? And again, minus here because we of course decrease. So this shows the decrease, and here is this is the how fast it decreases. So it decreases with the speed of the surface area. Again, this is the, for example, one can check that by hand, one can check that this is true for a lens, let's say. So this is just computable. So if you think about the lens, right, of which is formed by the circles of radius 1. If we start looking at the inner parallel bodies, it's always going to be again a lens, but of radius 1 minus t, of intersection of circles of radius 1 minus t. So here, this is my lens. Then here, this is my LT, right? And LT here is always the lens, which is intersection of circles radius 1 minus t. Okay. Again, this is in R2. This is not that hard to compute. So one can just write what the area of the lens here is going to be, and then differentiate it with respect to this parameter t, and see that it should coincide with the perimeter of this thing. Okay, but in general, so for all other bodies, this is the result, for example, which is due to Matheron from 78, which confirms that this is actually holds in any dimension and for any body case. And it doesn't have to be even lambda convex bodies. For any convex body K, this is satisfied. So the perimeter, the volume, the derivative of the volume of the inner parallel body behaves exactly like minus the surface. Okay, but if this is the case, then how do we obtain our formula above? So then if I know that the volume is differentiable, right, then what I can do, I can just integrate this Matheron's relation on the interval, on the admissible interval from 0 to r of k. Right? So if I integrate this from 0 to r of k, on the right hand side I have minus integral of the surface areas, right? But what do I get on the left hand side? And on the left hand side I have really just the value of the volume at the when time is equal to the in radius, and minus the value of this volume when t is equal to 0. Okay? At the time when t is equal to the in radius, this volume is just equal to 0. We have the degenerate body, as we said before. And at the time t is equal to 0, this is just the original body, because this is when we just didn't move anywhere, right? That's where we stayed. So then what here we have just minus volume, right? And multiplying by minus, we get the above. Okay? So this is the justification how I can write the volume in terms of the surface areas of the inner parallel bodies. Okay? So in some sense, I connect the volume with the surface areas. Right? For now, this inner parallel bodies, we will see that this is going to help. Okay, so what is the next idea? So if I have this connection, if I say something about the surface areas of the inner parallel bodies, in particular, what if I try to pointwise estimate this surface area and compare it to the surface area of the inner parallel bodies, but of my lens? Okay? So the idea here, I wish to show that something like this is going to be true. So if I take the surface areas of the inner parallel body of K, I would be very happy if I can show that they related to the surface areas of the inner parallel bodies of the lens in this way on the entire interval. Right? Because if this is the case, right, so let's assume that I have this, then what would I get? I would say that, okay, by my relation, the volume K here is just integral over all the surface areas. Pointwise, I can compare it. I can say that this is greater or equal than integral of the corresponding lens. Okay? And I will claim that what I have here, this is actually also the volume of the lens. Okay? So if I have this estimate, then I probably will be okay. So we're going to show that eventually it's going to hold. But this is the general idea where we want to have. So we want to prove something like this. Now, I claim that if we look at this relation, it's actually enough to show this relation only in the small neighborhood of 0. It doesn't even have to be on the entire, then it will follow. So my claim is that it is actually sufficient to show, let's call this star, to show this star around only in some small neighborhood of t is equal to 0. Okay? So why this is the case? Well, let's see. So if I have these two functions, right? The function that corresponds to the surface areas of K and the function that corresponds to the surface area of inner parallel bodies of L. So at the starting point, they coincide. Right? This is the condition in the theorem. When t is equal to 0, we know that surface areas do not change, right? They are the same, they're fixed. So here we know that dk is the same as the lens. Right? Now assume that I know that this relation holds around 0. Right? So around 0 I will know that, okay, the function for k, and this is my function dkt, lies above function for L. Right? Well, if they, on the entire interval, satisfy this behavior, then we don't have to worry about anything. But okay, let's say that they intersect the first time somewhere, right? Let's say that they, there is a point somewhere where they intersect. Okay? So let's say that this is some point t0. All right? So what does it mean that they intersect? It means that again at this point they have the same surface areas. Right? So this at this point, the surface area of K0 is the same as the surface area of L T0. Right? Okay? And what do I know? Well, then I claim that at this point I'm essentially again in the condition of this of my claim here, only not around 0 but around T0. And I can shift it always and repeat the same claim to argue that at this point they actually cannot switch the behavior. They always have to be, so this is the wrong picture, right? The correct picture would be that okay, maybe they touch, but nevertheless in this neighborhood still L has to be below K. Okay? And then we keep going. So then we can keep going and repeat essentially the same process, but if they at some point meet, right? But the most important thing that what we have that we will find some intervals in which they going to be strictly, one is going to be strictly above the other. Okay? Make sense?
Is it clear that this will be continuous function?
Say it again.
Is it clear that this will be a continuous function, or do you need some boundary assumptions?
Yes, it's this are continuous, absolutely continuous functions. So it's all good with that respect. It is known, right? I mean, one can have to show the argument, but it is known that this are absolutely continuous.
And something else.
Yeah.
If you wanted to show, is it clear that the irradiance of the length of the same surface area would be bigger than?
Good point. So it is not clear, and it is also kind of can be stated as a problem, right? Saying that, okay, if I fix the surface area, what body minimizes the in radius? And if I know this though, then it's just going to be clear. So if I have this, right, so what it tells me? It tells me that on the entire interval, right, to R, up to R of k, and up to R of k I still have the body, right, the inner parallel body. So up to R of k I know that k is going to die there, right, so, but L is going to be always have to lie below, right, and L dies at its in radius. So from here, you can say that you must have that R of k is greater or equal than R of L. They might coincide here, they might disappear at the same time, but at least we always know that on this entire interval they behave like this, right? So if I know this, I actually answer that question, let's say here in R2, right? So if I know the statement is true, then I can say that in radius is minimized on the length too.
Is there any curvature flow here?
Is there any questions, Mr. Arbet?
Curvature flow.
Curvature flow. I don't know, maybe. I'm not sure.
Curvature may not exist.
Yeah. Maybe you have to somehow do some weird things, but yeah, I really don't know. Okay. So good. So the only thing that is left here is really justify this claim, because once we have the claim, we have this, and then it's believable that I will be done here. So now let's work towards this claim. So let's state the proposition. So now the proposition, so what I want to show that this satisfies the inequality around t is equal to 0, and here there is a strict inequality unless k t is a length, but let's not bother. So I just want to show this. Inequality. So how to show this inequality? So what I know about these two functions, right? So I can think about this as two functions. Let's call it f of t, and this is g of t, right? What I know about these two functions is at the time 0, they're the same, right? So this is my general condition. Okay, so this is the fact that here my perimeters are the same. How to show that functions satisfy this inequality? Well, one way to do it is to show that derivatives of this function satisfy this inequality at t is equal to 0. This is the calculus exercise to show that if I have a function that coincides with 0 and the derivatives at 0 possess the inequality, then the function here are going to satisfy the same inequality. So want to show really that let's say here that the derivative of f at 0 actually satisfy this inequality. What happened? I tried, yeah, but it didn't work last time. But yeah, sorry. Trying not to press. Okay. So really, what I want to compare the derivatives here. Okay. So instead of if I compare the derivatives, I should be able to compare the functions. All right. Make sense?
Is it possible that the function f of t may be raised to 1 over m minus 1 power is concave, in which case you would know, in t, in which case you would know something about the second derivative too?
Is it possible that in t, I'm actually not sure about the second derivative, because with the second derivative, you have to be careful. So I can take the first derivative. With the second derivative, it might not be even, maybe because it's a surface area, it might not be even differentiable. There might be some issues. So, yeah. So from that point of view, you have to then just do it carefully, right? And
are those functions C1 or piecewise C1?
say again?
Like the functions that we're taking derivatives are they like C1 or piecewise C1?
So, well, they're kind of like piecewise C1 in this case, yeah. Because I'm working with this arcs, right? So.
So then the second. But I mean like the functions, like the cardinal, like size of the area.
Yeah. So I think they probably piecewise continuous, piecewise differentiable.
So they're concave?
I'm not sure that in general they are. Maybe you can show that they are, but.
I mean, maybe is it possible to use the fact that these should be shadow systems and then as the concavity system one knows that they are equal at some point, then the concavity is useful.
Are these shadow systems?
But I'm not sure that are they shadow systems, yeah.
It's always possible to write this kind of, when it's a continuous movement, it's always possible to write it in shadow systems.
Then maybe, I'm not sure. I think yeah. I need to look into that, yeah. About that, I'm not sure. Okay. All right, so good. So up to this point, also, I want to emphasize that I never used anywhere that I was on the plane. So that the formula for the volume holds in general for any body in any Rn, and all this argument about knowing only around t is equal to 0, it's also extendable to really to Rn. But this proposition is the place where I'm going to use that this is the plane. Okay, I mean in this case this is the plane. So if I want to compare the derivatives of this function, first I want to express this function. So I want to write down how the perimeter looks like. So let's focus on the situation. So I have the body K here, which is the all this intersection of the circles of radius. So I have the boundary consists of arcs of the circles of radius 1. Okay? So let's focus on the situation where the two such arcs meet. Okay? So here, so this is the arc of one circle, its radius, its center somewhere. This is the arc of another circle, its radius is also somewhere. Okay? All the circles of radius 1. So let me introduce a bit of notation. So let's say that each arc is subtended by some angle beta I. Okay? And let's say that two arcs here meet at the angle gamma I over 2. Gamma I just. Right? So I have the angles between the normals to two arcs here, right? And I have that every arc is essential of length beta I, right? Because the circle of radius 1, the arc is subtended by angle beta I, so the length is beta I. Okay? So in this notation, I can say that the original perimeter, so perimeter of K, is just the sum of all these angles beta I. Right? The sum of all the lengths of each arc. So this is just the sum of beta i's. Now how to find the perimeter of the inner parallel body in this case. So let me write it down and I will explain where this is coming from. So here I'm going to say that this is minus twice t times sum of tangents and then plus everything else of the order 2 or higher. Okay. So why do I really care only about the first order? Because I need to take the derivative at 0. So I don't really care the tail. Okay. So this is something of higher order, which is going to disappear eventually. Now, why do I have this relation? So let me first wave my hands, and then I'm going to prove that, well, I'm going to describe that, I'm going to come back to that at the end. So what is happening here? So here, if we want to look at the inner parallel body, we need to step inside by every normal by the distance t. Meaning, in this case, our normal is just the radius, right? So the line that connects center with every point on the boundary. So I step inside by t, right? And step inside by t. Again, I get the arc of the circle, but of radius 1 minus t, right? So if this was t, the entire radius is 1, so this arc is just the arc of the circle of radius 1 minus t. I do the same for the other curve, for the other part, something like that, right? And also get the arc of radius 1 minus t. Okay? Now, the part that contributes to my inner parallel body, it's really this part, without these two tails here. So really I need to eliminate these two, right? And the part that contributes to the inner parallel body, it's something here, and of course, at the other end, I'm also will have to remove the tails. Okay? So how can I compute this? Well, my idea is that, okay, I can compute the lengths of entire arcs, right? And such lengths exactly radius times the angle, right? Because the angle doesn't change, the radius changes, radius in 1 minus t. So 1 minus t times beta I is the length of this entire guy, right? And then I want to subtract this little tail. How to see that the tail really has this behavior? So again, if I want to just wave my hands, I can look at this picture a bit closer, right? So if I look at this picture, what do I have here? Let's say that this is my side, this side, and this side. Okay. So if t is very small, t is very close to 0. This is really almost like a segment, almost like a line. So let me for now treat it as a line. Okay. If I treat it as a line, so what we have here, that here I have the right angle. The angle that I have on this picture is just half of the angle where the normals meet by the symmetry here. So this my angle really just gamma over 2. Okay. The side by which we stepped inside is this is my t. Oh, I drew it. Oh, this is my t. I need to flip it.
It's exactly half?
It's exactly half, yeah.
Or you can use yellow color.
Wait, sorry?
You can use also yellow color in there.
Oh, I can use, yeah, I can use the yellow color. But the point is that what I'm getting here, right, this side is exactly t times the tangent. So if really I believe that this is almost like a right triangle, then this, in order t, this should probably give me the behavior. So that's why here, well, again, one can believe that that might be it, right? We will later show it precisely that exactly in t that this is the defining behavior. Okay. So this is for now. Let's assume that this is our formula, and let's finish the proof, and then we will come back to this. Okay, this is just a technical point. Okay. So if this is the formula, then what do I need? I need to compute the derivative. Okay. So let's take the derivative of this expression. So let's compute the derivative at 0. So what do I have? So here I have, from this term, I have minus sum of beta i's, and from the second term I have minus twice sum of tangents. The tail disappears, at 0 it's 0. Okay. The tail contains all the terms of higher order. So this is my expression. What I note that in this expression, this first term is really just the perimeter of K. Right? which is, as we know, is fixed, right? It's equal to the perimeter of the lens at the start. Okay, but now, of course, I can repeat the same thing for the lens too, right? So I can do the same computation for the lens. In case of the lens, I actually know that if I have the lens here, right, the lens has really only one angle, right? It is symmetric, and its angle where these two arcs meet, let's denote it by gamma star. Okay? So I have gamma star here, I have also gamma star here, right? So it's really only corresponding, for the lens I really have only one angle. So then the same computation will give me minus the perimeter of L, and then minus, so what I have here, I have minus twice tangent of my gamma star over 2, but I really have to multiply by 2 because I have 2 vertices here. So at each vertex I will subtract the 2 little tails. So I have the 4 tails in total. So this is here equal to minus 4 tangent gamma star. Okay? And this is the lens, right? So this angle gamma star corresponds to the lens L here, such that it has the same perimeter as the K. Right? So this is my optimal lens, right? The one to which I'm going to want to reach. Okay? Make sense here?
Shouldn't there be a T as well?
No, I took the derivative, right?
Yeah, I took the derivative.
I took the derivative, T disappears,
Okay.
right? So here, if I would write this properly, right, that would be T. Okay, so I have this expression. Now, what we know, again, we know that these two, they're really the same, right? The lens, the perimeters at the starting point are the same. So if I want to show that the derivative of K is greater than derivative of L, I really need to care about this second term. Right? In other words, if I multiply also by minus sign, so what I want to show that the sum of twice and divide by 2, so the sum of tangents less or equal than twice the tangent with the angle of the lens. Because I want to show that this is greater than this, but then with minus sign, I need to show that this is less than this. Okay? So I need to optimize the left-hand side. And essentially, while optimizing this left-hand side, I need to show that left-hand side is optimized on the lens. That's the state. Okay, so now the question is, all right, so I have some function in terms of all these angles. I need to optimize it. So what do? I need to get some constraints under which I can optimize. So the question is how to optimize here the left-hand side. So I'm claiming that because of our geometry here, we can actually get a few constraints that will be helpful here. Okay? So the first constraint comes from the general fact that the spherical image of a convex curve is equal to 2 pi. So why this? Well, again, let's look at the lens first. Okay, so if I have the lens, I know that here the jump, so where the normals meet at the angle gamma star, right? So if the curve is convex, then really, if you take the unit normal at every point here, right, and put this unit normals on unit circle here, you want to see what they span there, right? So how much of the circle we are going to walk through. So if the curve is convex, we're really going to walk only one full turn here, right? But then which turn so what we are doing? We are starting, let's say, at this point, right? We take with our normals, we walk this angle. This angle corresponds to the angle that is this arc is subtended, right? Which is just, in our case, right, the length of this arc here. Then I will have a jump, right, the angle gamma star. Again, I walk the same length, right? And again, the jump. So really what I have here, I have the perimeter of L, right, plus 2 jumps, plus twice the angle gamma star, which has to be equal to 2 pi. Well, the same situation is going to happen if I have more arcs, right? Again, while I walk along every arc, it's going to I just walk the angle, right, that this arc is subtended by. But this angle is exactly the length, right? That's how we define it. We have all the circles of radius 1, right? So the same story can be repeated for k, but then of course I have to maybe jump more because maybe I have more vertices. So at every vertex, right, I have the angle gamma I, that's the jump. And this is also equal to 2 pi. Okay? Well, again, the life is that the perimeters are the same. So from these two conditions, we get one restriction that the sum of these angles has to equal to twice the angle of the corresponding length. Okay? So this is one condition. Now, let's see the second. So the second condition essentially follows from the Blaschke-Roland theorem in some sense. So what do I have here? So let's say, again, I focus on two arcs of when my two sides meet. So let's say that I have these two arcs, right? And here I have my, well, maybe there are more vertices, doesn't matter, right? So by Blaschke-Roland theorem, I know that such lambda convex polygon sits in the balls of radius 1, right? So in particular, I can extend this part and I can extend this part of the circle, right? And the intersection is going to contain this polygon K, right? Now the intersection gives me again a length, right? And length with the angle gamma I, right? Because that's the original polygon. At the vertex, the normals meet at this angle gamma I. So this gives me the length of with the corresponding angle gamma I. Now what I know about this length. This length definitely has the bigger perimeter than this polygon K. Right? So the polygon, it contains the polygon K, the perimeters, Dylan was telling us yesterday that the surface area is monotone, right? So this perimeter of the lens is larger than this optimal perimeter, right? The perimeter of my guy K. So what I can do? Well, I can take this lens and start shrinking it until I get to the same perimeter. Right, so I can start shrinking them. When I shrink this to, right, when I move closer to circles in this case, the angle where they meet at the normal is going to open up. It's going to become larger, right? And I need to shrink it until I get the same perimeter as here. But once I reach the same perimeter as here, the lens is defined uniquely. So that lens must have this angle gamma star. There's no way around it. So meaning that, okay, usually, essentially applying the shrinking process, this angle cannot exceed the corresponding angle of the lens, of the optimal lens, right? The lens that have the same perimeter as K. Okay. So, but of course I can do this for any such vertex, right? The vertex doesn't matter here. So meaning that every such angle, so the maximal of all these angles cannot exceed, so any such angle cannot exceed the angle for the lens. All right? And this is going to be my second constraint. Okay? Make sense? Right? Okay. So now, once I have the constraints, let's try to finish. Let's try to optimize this function. All right, so now I have two constraints, and I have the function which is sum of tangents. Okay? So I want to optimize it. So let's look at this function. Okay? so the trick what I can do, I can take this each tangent and divide and multiply by its angle. Right? So I don't change the function at all. So I can rewrite it as the angle times tangent over the angle. Okay. Now, the nice thing that look at this function here. This is really I can look at the function tangent x over x, and this function is increasing. So this function is increasing. If it's increasing, I can, for each gamma I, apply this condition too, right, and pass to the angle gamma star. So for each such function here, I can say apply the second condition, right, that what I have sum of gamma over 2, so this is remains, right? And each of these guys I will replace with tangent gamma star over 2 divided by gamma star. Right? So, which is, it doesn't depend on the sum here, so I can take it out. Gamma star over 2. Okay. But now I can apply the first condition, right? The first condition tells me that sum of angles gamma I has to be equal to twice gamma star, right? So really, this part is just equal to gamma star, right? So here I apply the first relation, right? And gamma star cancels, 2 comes up, and I have twice tangent of the corresponding angle of the lens, right? And it's exactly what I wanted to show. Okay? So this here, by model of the fact that I wave my hands how to find this part for now, I'm going to come back to it, right? This finishes the proof for this one convex polygon. Okay? Make sense? Okay. Well, okay, this finishes the proof. Let me just, well, in one part. So let me go back, right? So what this finishes the proof of the proposition definitely, right? So the proposition tells me that the area of the KT is greater than area of LT, right? So if I go back to the expression that I had for the volume, right? So this is indeed, I get what I want, right? I can say that this is from 0 to K of the corresponding length, right? And this is exactly what Beatrice was asking. So here, the integral from 0 to R of K, but really this is the integral from 0 to R of L. Because the proposition will imply that, so proposition also implies that R of K has to be greater than R of, the in radius of K has to be greater than in radius for L if we have the fixed surface area. Okay? So in some sense, the proposition also tells me that among all such one convex polygons, length also minimizes their in radius. Okay? So here, as I said, really this can be put in radius of L, and once I put in radius of L, then this is clear that by the same formula, this is the area of L. Okay? And now this is by modulo this part, this finishes the proof of this theorem. Okay? Any questions here?
So I should make sure I understand. So from the Blaschke-Rolling theorem, that's one step is sharp with equality if and only if K is the spherical.
Yeah. Right. Okay, so let me go back to this part that I skipped. So, well, as I said, it's believable that this little tail that we need to subtract has really the order T has this behavior of tangent gamma over 2. Now, let's show this quickly. So, let's focus on one arc. So I have this one arc, and I have the, let's say, the yellow arc. So here, really, somewhere I have the center, right, of these two circles. Here I have, so this distance, really distance T. Now I want to subtract some tail here, right? So let's say this is the tail that I want to subtract. I'm going to connect this point 2 with the center, right? Because again, we walk inside along every radius here, right? Along every normal. So this is just the part, right? This is the little tail that I need to subtract from the yellow line. So, and well, this is, right, this distance is really 1 minus t, right? And the same with this side, this is also 1 minus t. Now, where's my angles are, right? For the angles, I know that I connect here. This is my gamma over 2, and this is my gamma over 2 from the above picture. And what I want to find the length of this little part x of t. Okay, let me introduce this parameter alpha here, also the angle. So if I look at this little piece x of t, this is really just the radius times by this angle it is supported by. Okay. What I know about them? I know that at 0, the species must be equal to 0. Right? At 0, this is exactly when we do not move at all. Right? So they both equal to 0. I want to express x, so expand x in a Taylor around t is equal to 0. Right? So what I have that x of t should be x of 0 plus x prime of 0 t plus everything of higher order. This is 0, so this doesn't matter. Right? What is now x prime at 0? Well, x prime at 0, if I differentiate here by product rule, really just give me alpha prime of 0. Exactly, because when I differentiate this part, alpha of 0 is 0, right? So that disappears. So this term really equal to the derivative of this angle. Okay? So now what I need to know what this derivative of the angle is. And I can get it, let's say, from this triangle. So if I say, let's say this is point A, this is point B, and this is point O. So I have this O, A, B. For this side, the angle here is gamma over 2. The angle here is exactly this alpha. This side is 1 minus t. This side is 1. Okay. So by law of sines here, well, I want to describe alpha, right, in terms of t here. By law of sines, what we have here, so we have that sine of the angle gamma over 2 over the side length, which is 1 minus t, right, is equal to, I know this side, so I really need to know just this angle, but this angle is pi minus this 2. Right, so here I have sine of pi minus alpha of t minus gamma over 2 over 1. Right. All the sine here, pi minus this angle, is again sine of the sum of 2. So this is really just sine of alpha plus gamma. Okay. And from here, I can find what the alpha prime is. Right? So if I take the derivative, so if I differentiate with respect to t, I get sine gamma over 2 over 1 minus t squared on the left. And on the right, I have cos of alpha plus gamma over 2 times derivative of alpha. Okay. So now when t is equal to 0, this is equal to cos of gamma over 2, this is equal to sine of gamma over 2, and this is equal to 1. Right? So exactly when from here, when at 0, alpha is precisely the tangent, and that's exactly what we need here. So this is the this is properly how one can properly justify that this tail, little tail, indeed has the order of tangent gamma over 2 in the first order in the P. All right? So this finishes the part with the two-dimensional case. So in the next lecture, I'm going to describe how can we readjust it to the three-dimensional case and what works and what doesn't work. Okay, I will stop here. Thanks.